Yes, welcome all. My name is Stefan Flügel. I'm a research economist at the Institute of Transport Economics here in Oslo. I'm the initiator and the project manager of the PRELONG project, which started up just a few weeks ago. Today I want to give a thematic introduction, and I want to present the research questions, and then I will outline our approach. And in particular, I want to talk about agent-based traffic simulations, which we are going to use to generate training data for our machine learning model. And then I will talk a little bit about the design of our tool, which we're going to build in this project. And last but not least, I'm presenting the overall project and also the PhD project, which is part of this project. So the short title of our project is the AI Traffic Planner Project. This is not the official title. The official title is Machine Learning for Computational Efficient Predictions of Long-Term Congestion Patterns in Large-Scale Transport Systems. And the acronym is PRELONG. So I'm now going to go through the main terms here in this title and explain it to you. So the term traffic planning is maybe not so good established. More common is to use the terms long-term transport planning, which is opposed to the more day-to-day transport or traffic management. So on the national and regional level, we typically do investments in the infrastructure, which would be part of the long-term transport planning. And traffic management is most relevant in cities. But there's also, of course, long-term planning for cities. And this is then mainly the main roads in and out of the cities and also within the cities. And on the national and regional level, we are most interested in when we're looking at the road market, we are most interested in the capacity and connection of motorways. And this is quite different from the management, the signaling and the ITS of the daily traffic flow. So the term traffic planning in our case would be located somewhere here, where we are mostly interested in long-term planning, mostly interested in the city or the metropolitan areas, and mainly interested in major roads. And there is some class book categorization of transport models. Strategic transport models, they are more bigger models for the whole country or regions, where you predict long-term demand effects. And this is opposed to operational transport models, which have a shorter time horizon and are more detailed, but are on a much smaller scale. So they are like on city districts or roundabouts. And the tactical transport models are somewhat in between. There you model some parts of demand, but not necessarily the long-term demand effects. When it comes to operational transport models in Norway, we have a strategic transport model system called NTM-RTM, which is widely used for transport planning and appraisal. And on the other side, we have the traffic simulation models like AIMSIM. And you can argue that there is no operational tactical transport models for road traffic. The railway authorities have a tactical transport models for rail traffic, where they predict the demand for different departures of trains and then model the resulting congestion level or crowding level in that case. And what in practice then happens is that you're trying to use the strategic transport models to do prediction in cities. So you're using a strategic transport models for tactical purposes, and I will come back to that later. So what is congestion? Well, congestion is the situation where cars have to reduce their speed in order to not hit each other, right? So this figure explains what happens when more and more cars enter a highway. So in the beginning, you can drive at full speed, so close to the speed limit, and then when more and more cars enter the link, eventually you have to decrease speed, and this is where we get the congestion in the system. And then when you're coming close to the maximum traffic flow, you have a situation where you both decrease speed and decrease the throughout through the link when more and more cars enter the link. So this is what we call hypercongestion. And it's interesting to note that there are no good mathematical functions on a macro level that describe hypercongestion. So because at a given traffic flow, you have in a way two speeds which are consistent with the function. So what you do in practice in the strategic transport models is to assume a function like that, where you in a way allow for the traffic flow to exceed the physical limit. So this is not an ideal way to model congestion. It basically only models delay as a function of reduced speed. So in the best model solution is to do simulations of the micromechanisms. Yes, congestion, to give a more practical motivation, of course, causes longer travel times. So this leads to delays. And of course, a loss of leisure time. And so there's an opportunity cost of traveling, right? So people would rather like to come earlier than later. So there's this loss of leisure time. And another aspect, which is often ignored, is that there is also a comfort effect of being in congested travel. So here we have some values which we estimated from static preference data showing that people have a much higher willingness to pay to reduce a given minute in travel when it's congested. So overall, we have a higher willingness to pay to reduce congestion, and this is reflected also in the external costs of driving, which amounts to 2.6 billion krones a year. This is more than 1% of the GDP in Norway. Long-term congestion. So I think congestion will increase in the future. We have general population growth. We have urbanization, which leads to more people living in cities and need to travel in cities. You have also the typical increase in car demand due to increase in income. So more and more people can afford to own a car. And there's also technological things which most likely will lead to an increase in car demand. So in a scenario of robotaxis, for example, these are likely to be able to operate on a much lower cost than the current taxi solution. So it's likely that the demand will increase. You can also imagine a scenario where children and young people can use the car alone. So this would enlarge the user case. And also you could argue that, and we have some empirical evidence for that the value of time is lower in automated cars because you can use your time more effectively. You can basically sleep if you want. So we did some simulations with that and showed that the market shares for car can increase quite a lot in scenarios with robotaxis. So in the Oslo metropolitan area, we have like about 50% car market share, and this could increase to close to 60% as predicted by these models. Okay, so what is a transport system? We regard transport system as complex systems. So we have millions of moving parts, cars and people and freight, and there are physical dynamics, right? So you have bottlenecks in particular, and it might be difficult to predict what a bottleneck can cause, like some upstream of the network. And well, transport systems are also complex because humans are complex and have different preferences and needs and limitations, right? So it's very difficult to predict human behavior, and in addition, you have many interactions which are difficult to model. So from our perspective, congestion is then an emergent property of a complex system. It's in a way, it's due to microscopic behavior, but it only shows in a way at the macro level. And the main research questions for our project is, can we reliably and quickly predict the macro state, so congestion patterns, without explicitly simulating the underlying micromechanisms? I will come back to that question and motivate it more from a method point. So large-scale transport systems, in our case, is the Oslo metropolitan area. Here's a map shown from Google Maps. And so our focus is on the overall traffic patterns, which are relevant for transport planning. And here we are most interested in not what will happen after, for example, an accident, which would be a shock to the system, but we are more interested in congestion patterns under some stable conditions, so maybe close to an equilibrium, right? And we are also mostly interested in major roads. And the purpose is to be able to identify needs for long-term investments in infrastructure. Okay, now we're turning to AI. What is AI? Maybe starting by what is intelligence. There are many definitions. My favorite one is by Joshua Bach, who is my favorite AI researcher and philosopher. And he says intelligence is the ability to make models. And then he explains further that models is something that explains information. And information is what we perceive at the systematic interface, or at our brain in the human case. And then we make meaning of the information by discovering changes in the information. So we're receiving waves of sounds and light, and then our brain has a model of that and interprets that as sounds and colors. So as Joshua Bach says, there are no sounds and colors in the physical reality. That's only what the models we're making out of the sensory data we are getting. And we can also define a mathematical model as a simplified description of a system or process to assist calculations and predictions. And the important word here is simplified. So we want to have a reduced version, right? We in a way want to comprimate data. So another definition of intelligence is the ability to make data compression. So what is then artificial intelligence? Well, maybe we can define it by machines that are able to make predictive models. And we can distinguish between general AI and narrow AI. And today, most AI systems are narrow AI. They're good at building one or few models and completing a limited number of tasks, right? Yes. So machine learning is a subset or a part of AI, and it is can be defined as computer algorithms that can improve automatically through experience and by the use of data. Yes. So you can show it like that. So ML is the more induced part of AI. So there are other parts of AI. And within machine learnings, you have a type of algorithms which is called neural networks, which basically is a system of neurals, and they are activated by some weights and biases, and they in a way mimic the human brain to some extent. And within neural networks, which have shown to be very efficient in doing a quite variety of tasks, you have different subtypes of neural networks, and the two subsets which are mostly interesting in our case are binarized neural networks, where the weights are binary. I will come back to that, but it's basically the weights in your neural network are either -1 or 1, and this saves a lot of memory and can increase computation times. And maybe more importantly, there is a type of neural network which is called graph neural network, which uses graph data, and of course transport networks are graphs. So this is fits our purpose very well. And then there is a combination of that, which would be called binarized graph neural networks, and the PhD project is looking into these type of models, which are not very much explored at the moment. So machine learning for transport planning and modeling is increasing, as this graph shows. It's very trendy to use machine learning, but I think it's also very useful. And when it comes to machine learning for congestion patterns, I'm sure there are a lot of papers around that. I can just show you something we did at TUI in collaboration with master students. So the research question was there: can we predict citywide traffic flow with simple deep neural networks trained on limited counting data? And we used the counting stations in the Oslo area to train a model. And this is the result on the test data, which looks quite promising. And then we used this neural network to predict the traffic flow on the whole transportation network. And we got rather promising results, I would say. So we recognize at least the main roads here. So to some extent, we were able to generalize the data from the counting stations to the whole network. But of course, there are limitations to that approach. And in particular, you can't really use that for transport planning because it only reflects the current situation. And when you want to predict the future, you have to have a higher variation in the training data, right? You need to include scenarios where the population has grown, or there's different capacities in the network, or maybe different road tolls and so on. So the last term I want to explain is computational efficient. Well, first we can state that most transport models in Norway and other places, they are typically not user-friendly. So you typically need an expert to run the models, and there's often no or poor result visualization, and especially there are long running times. So the regional transport models in Norway, they take several hours to run, and if you have a version which is much segmented, then it can take 2 days. So what can we expect from machine learning? I don't know, maybe minutes, maybe seconds. In any case, so I regard this project as a project towards truly user-friendly transport models. So this is in a way the ambition. We have to see how we will do. So just restating the main research question once again. Can we reliably and quickly predict traffic flow and hypercongestion in a road network using a machine learning approach? That is, without explicitly modeling underlying behavioral and physical mechanisms, such as route choice and vehicle propagation. And related research question is around the use of agent-based traffic simulation models to use as a way to generate training data. And then we have other research questions, one around the binarized neural networks, which I come back to. And then one question is, how fast can we do that, right? And then we have more applied research questions regarding future bottlenecks in the Oslo road network, and whether or not we can identify some general drivers of hypercongestion, which goes beyond the Oslo case. So, but I will spend a little bit more time on this first research question. Can machine learning models trained on agent-based traffic simulation models be used to make long-term predictions of traffic flow? So this is the typical high-level process flow. So you have some raw data, and then before you put it in a machine learning algorithm, you have to structure this data to some extent. And what you get out of the machine learning model, what you get out of the machine learning algorithm is a model, right? So the main idea here is to use simulation to generate raw data. And why would we do that? Well, real-world data has not enough variation to capture the wide range of possible futures, right? So what happens in 30 years in Oslo will depend on how many people are living in Oslo at that time, right? And you don't have, the current data does not show this scenario. And as a side note, this is using simulation to generate data is very common in machine learning. The most simple one is maybe data augmentation, right? Where you simulate different lighting effects, or you simulate rain to be able to be more capable to predict if a picture is a cat or not. You have also these chess AIs, and they, when they play, they simulate a lot of alternative moves, right? So they in a way simulate different futures. And maybe the most practical one are these driverless cars. Here, this is from a Tesla presentation a few weeks ago, where they train their cars on both real-world data, and they also generate alternative situations or hypothetical situations in these simulators. So this is important in that case to simulate edge cases, which are not often observed in the real world. But in our case, it's really about to have a higher variability in the data, such that we can predict a wider range of possible futures. So to motivate more the use of agent-based models, I have to talk a little bit about transport modeling systems. So the transport model system is basically a combination of a physical model of network flow, which I, as an economist, like to call a supply model. And then we have a behavioral model of travel demand. And this is only half of the picture. This is a very famous flow chart here. And just to illustrate that, so the demand model captures route choice, mode choice, destination choice, trip choice, car ownership choice, whilst you have to assume something to be exogenous, and this is often the activities of the population. And the physical model of network flow predicts then link loads and travel times, right? And then you have an iterative process where this is explained by this and this is explained by this. So there are also some interesting modeling perspectives here from a paper by Peter Jones, which I very much like. So the modeling, transport modeling started in the 50s and 60s with a vehicle-based paradigm, where you basically use the laws from physics to explain transport, right? So route choice was explained by taking the shortest path, and demand was explained by some gravity models where demand is a function of the size of cities and the distance between cities. And then by the 70s, by the rise of logit models, right? Daniel McFadden, you had a shift in perspective, and you started to analyzing choices of humans, of decision makers. And then there's another extension, which is called the activity-based approach, which is quite relevant here, actually. So the activity-based approach recognizes that demand for transport is derived from the demand of activities. And in order to understand transport, you have to understand the activities that people want to perform. And then there's the attitude-based approach, which in a way includes some further elements, more psychological or sociological elements into the modeling framework, which is not very common to use in practical transport models. And then you have a dynamics perspective, which in a way includes that transport systems are really complex. And so when it comes to modeling elements, our strategic transport models, regional transport models, RTM, they in a way capture the first elements here: vehicle ownership forecasts, trip generation, trip distribution, mode choice, and traffic route assignment. So, and the activity-based models, they include also the choice of departure time as an important element. And I don't think it's in the paper by Jones, but I think there's some parallel to the field of economics, where you have neoclassical economics, behavioral economics, and then as the latest trend, complexity economics. So what is complexity economics? I think one of the founders is Brian Arthur, and he's also the creator of the alpha par problem. The problem is very simple. You have 100 agents, and every agent wants to go to a bar, this alpha bar in Santa Fe, I think. And but agents do not want to go there if it's too crowded. So say if it's over 60 persons at the bar is too crowded and it's not pleasant anymore. So what is the outcome of this problem? And it's interesting to see that you can't deduce a result here. All pure strategies fail in a way. If you think the bar is not crowded, you will go, and then everybody goes and the bar is actually crowded, right? So you need to solve this problem. You have in a way to model different strategies of individual agents. And this is shown in this graph here. And what is shown here is that these systems, they tend to find an equilibrium pattern around the comfortable value. And there's like an ecology, right? So people form expectations, then they experience what is happening, and then they're adjusting their behavior. And what one often sees is that that leads to quite stable results, which is quite nice, I think. So here's just a table, which is very nice. I don't have the time to go through all the elements, but I think transport is best understood by complexity economics and not by neoclassical economics. So agents are very different, right? They have different motivations, different needs. Some do seldom travel, some do travel a lot. They have to pick up their children at kindergarten and they got to work, and so agents in a transport models, travelers, they in reality are very different, and they react to aggregated outcomes, right? They react to the congestion patterns, and they experience congestion, they learn from that, and then they adjust their behavior. So yeah, I think complexity economics fits very well to the transport problem. And also the method to solve problems in complexity economics are a type of models which are called agent-based, which are computational models, right, to simulate the actions and interactions of autonomous agents. So these are really micro models, but the typical goal is to understand behavior at the system level, so at the macro level. And there is these agent-based transport simulation models where you simulate travel behavior at an individual level, and you simulate what happens in the network. You have a dynamic simulation, and agents experience the system, the congestion, right? They learn from it, and they explore different alternative strategies. They can switch transport mode. They can choose to depart earlier or later to avoid congestion. And when you run that a long time, agent will learn and adapt, and there's often some equilibrium pattern which arises. And this is then congestion as an emergent property, right? So to be more precise, we are going to use METSIM, which is an open source framework for these type of multi-agent transport simulations. METSIM has an advantage that is applicable for very large scenarios, so up to 5 million agents, 10 million agents maybe. It's also an academic developer team and has a long tradition and is used over the whole world. So in METSIM, you have two main inputs. One is the network, the transportation network, which represents the supply side. And then you have the plans of the agents. And an agent has such a plan which describes what this agent is, what he wants to achieve for the day, what type of activities he wants to perform. So this agent with that ID is starting at home at this location, and then at 7:07:11 he takes the car to work, and the work is located at that coordinates, and then he's at work till 16:41, for example, right? So you have a static population of many of those agents, and every agent wants to perform his or her activities, and so this is then simulated in the simulator. And when the day is done, right, when you overnight in a way, agents then evaluate how it went, if they arrived at the destinations at the desirable times and didn't experience much congestion, they will score. They will give a high score for the strategy they used, and but they will also explore different strategies, and maybe they will change behavior or the plans from one day to another, and then you simulate maybe 100 days, and you observe an equilibrium pattern there. It's not a theoretical equilibrium, but it's in a way a more or less stable situation. And then you interrupt the simulation or the algorithm, and you receive output data. And the most central output data are the so-called event files, which save in a way a second for second description of what happened on that day for all the agents, right? So an agent would leave the house, he would enter the car, he would enter a link with that car, and so on. So this is all stored in these event files. And these event files are basically our raw data, which we are using in our approach. So here's just an illustration of some event files. It's a little bit bad quality here. So each dot here is a car. This is the Trondheim area from our model from 2014. And then here you see how congestion is building up on a motorway south of Trondheim. So this is a quite different approach to the strategic transport models, where you have more aggregated quantities which you are operating with. And the philosophy is also very different, right? So the RTM system is more a vehicle and personal based approach, while METSIM is more activity based. And I would argue that RTM is mainly following classical economics. You have you're basically minimizing costs and maximizing utilities. So this is formalized as a mathematical program, right, which you solve more or less analytically. While METSIM is a simulation model which is based on computation, right? So, and I think this is a trend which also is in many disciplines, that you're using more and more computational models to capture the complexity of the system. The algorithm is called co-evolutionary because the plans of the different agents, they co-evolve over time. And from a more practical point of view, it's important to note that the RTM model system has some advantages, in particular that it includes long-term decision makings like destination choice and trip frequency choice. However, it is a static and macroscopic model and has therefore an unrealistic modeling of congestion. And it's also a quite inflexible model system, so it's quite expensive to further improve on the model system. However, the RTM model system is operational in Norway. There exist many different types of models, and together they cover the whole of Norway. So it's widely used in transport planning and appraisal. So the METSIM is in some sense a less established model system, and there has only been some few and minor pilot projects in Norway. And the big advantage is, of course, you have dynamic and microscopic topology of your model system. And in comparison to Aimson and other classical simulation models, you have also mode choice and departure time choices as choice elements. So you're capturing some part of the demand side. What are the practical challenges for METSIM? It's, I would say, calibration. It's also also the running times are quite high, and of course you need expert knowledge to run those models. And actually these three types are the things we want to address in our project here, because by using machine learning we hope to reduce running times. We hope to get a more or less automatic calibration, and we also plan to have this AI tool to be much more accessible than current transport models. So this is the structure in the transport models. In the traditional transport models, you're in a way iterating between a demand model and the network assignment package. And in a way, each iteration is one optimization step. So you're trying to optimize a network flow given demand, and then you're trying to optimize demand given network flow. And then you iterate, and then at some practical point you stop, and then you regard that outcome as the equilibrium. In the agent-based model, route choice is part of the demand model, and you're iterating between the demand model and the network flow model. as I just described, in a way, doing one day by one day, right? And then you're learning overnight, so to say. So each iteration can be understood as one learning step. And this, in a way, brings us back to machine learning and the different types of machine learning. So you have supervised learning, right, where you train your model against some known output or outcome. And if the outcome is continuous, you have a regression model. And if the outcome is discretized, you have a classification model. And then you have unsupervised learning, where you don't have a clear outcome, where you more or less try to learn structures in the data set, more or less on its own. And in reinforcement learning, you have an bot or an roboter who tries to figure out things and learns by mistake. And this is in a way analogous to our agents in the agent simulation, right? So the agents in our simulation, they're in a way doing some reinforcement learning by trying out strategies and getting some feedback and then having a feedback loop. But we will use in a way reinforcement learning within the simulations, and then we're doing supervised learning on the output of the simulations. And for example, a regression problem would be predict the traffic flow and average speed on road X at time of day Y in forecasting year Z. So this would be something we could learn from our machine learning model. And classification would be quite similar. There you would just classify road X at a certain time as free flow, congestion, or hyper congestion. So we haven't really decided what we're using. We have to figure that out. But coming back to this high-level process flow, we will also have some calibration, of course, of the simulator, which we can use from the AI model, but also directly from the event files. But the thing I wanted to stress again is that in a way we have a loop here within the simulation where we have plans, simulation, performance measures, and reinforcement learning. And then this step is supervised machine learning. And the AI tool then basically you will be allowed to define scenarios, right? And this is then feed into the model, and then you get scenario results. And if we revise the, if we revisit the research question, so the question is, can we go from scenario definition to scenario results without going into the micro mechanisms, right? So we have micro here and here, but we would have macro here and here and here. And can we go from macro to macro with machine learning? This is basically the question I'm mostly interested in this project. So this traffic planner tool, it would be some sketch planning tool, mainly for transport and city planners, and probably mostly used in the early phases of what infrastructure investment. So the idea is to be able to use that tool to identify weaknesses in the current network and to anticipate the future bottlenecks. And our vision is that this is truly user-friendly, fast, easy to operate, and easy to interpret. And of course, it should be somewhat reliable and consistent. But this, of course, we have to see how we do. We imagine that this will be some web application. This should be open access. And the idea is to have some graphical user interface, some input map, and then some GIS-based visualization, some output map. So this is how it could look. Just an early idea from my side. This can, of course, be improved or changed. But the things you could change here is the forecasting year, right? You can then change all these parameters, additional car demand, overall scaling of road capacity. This is might be interesting if you want to simulate scenarios of driverless cars, because you can argue that the technology will increase road capacity. So you can play a little bit with these assumptions here. And then you can also click in, this is at least the idea, to click on single links and change the parameters for that link. So the road capacity, the speed limit, and the road toll. These are in a way the parameters which we can manipulate in MetSim, and then we have to run the scenarios or the simulation such that we cover the whole spectrum of possibilities here. And on the right side, you would then be able to visualize the results by color codes and by clicking on single links. And of course, congestion is dependent on the day of time, so you could also then click here through different time periods throughout the day. Okay. Yes, so last but not least, some general information. So the objective is, as I said, develop and build the AI-based sketch planning tool to improve our understanding of congestion patterns and advance AI-based transportation research in Norway and other places. And the main outcome would again be the sketch planning tool, and of course also the PhD project and related scientific publications. So we have a PhD project at the Department for Informatics at the University of Bergen. Grunde Wesenberg is the candidate, and the main supervisor is Associate Professor Anna Osaki. And a rough plan about the PhD project would look like first a review paper on machine learning applications in the transport area, and then a theoretical paper on the binarized and binarized graph neural networks, and then a paper about the overall implementation of that approach, and then a paper about the interpretation of the model. And there are some particular ideas to use binarized neural networks to be able to get some propositional logic out of the neural network. So the binarized neural networks, as I said, the weights are just one bit of information. So it's either -1 or 1. And this is compared then to real valued neural networks, which is the normal case. So this is a question speed versus precision. But as I said, the binarized neural networks, they allow also encoding into prepositional logic. So the idea is to, if it's only -1 and 1, then you can say, okay, this node is activated when this node is activated, when this node is activated, right? And then you can translate that into logic. And the idea is that the neural network is then less of a black box to the researcher. And then the question about graph neural networks. I mean, as I said, transportation networks are graphs, and graph neural networks then embed the data structure from the networks in a way that it increases consistency, right? Because when you look at traffic flows, there's a high spatial and also temporal correlation, and in a way you will capture that with a graph neural network. Yes. So yeah, we just started up, as I said. We have 4 years. This is mainly funded by the Norwegian Research Council, and it's within the IKT Plus program, where the idea is to promote cooperation to develop R&D expertise and capacities. So we have 4 partners here today. We have the University of Bergen, the Swedish National Road and Transport Institute, the AI-company Epigram, and the Norwegian Public Road Administration. So I think this is a very nice mix of partners. We have both applied research and academic research, and we have development, and we have policy. And these are the people, the researchers who are involved in this project. So we have up here, we have transport modelers. Down there, we have AI researchers. Here we have data scientists and well, the people from the Norwegian Road Administration, they have different background, but mainly transport analysts and planners. And this is just to give an idea about the work package structure. So we have started with VP1A, where we generate a network and gather real-world data for calibration. The PhD project has started and has started looking into theoretical considerations. We have started with the data integration subtask, where we want to have a toy version run through such that we can plan and manage the data flow. And then we have started to think about the design of the AI tool. Right. So we will have this webinars once a year, I guess. And I think we will establish a YouTube channel where we will show some simulations and maybe explain also the tool and so on. And well, you're very welcome to give feedback about the method and from a practical side also on the design of the sketch planning tool. And well, you're welcome to contact us. And I'm willing to take questions now from the audience. Hannah, are you with us? Yes.
Yeah. I will just stop the recording.